Yeah. Test 1, test 2.
Awesome. Welcome to Melbourne CocoaHeads 183. I think I'm visible. Yeah, okay, great. Oh, that's what I forgot. I'm Pat, thank you for coming. In the spirit of reconciliation, Melbourne CocoaHeads acknowledges the traditional custodians of country throughout Australia and their connections to land, sea and community. We pay our respects to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islanders people today. Okay, it's going to be a short but sweet session. Steve Pry's doing a talk tonight on what the L is SQL. People are saying he is the David Attenborough of computer science. That's what I've heard anyway. We've got a code of conduct here at CocoaHeads. We want to make people feel inclusive and safe. So if you see anyone feeling uncomfortable or, something's not right, I think we're cutting that off. Gina, can you hit the little local P, like the pip thing next to the other one? Yep. Oh, yeah, no, not that one, not that one. Back out. All right, abort. We'll get that link to someone later. But it says code of conduct. If we're doing fine. Some housekeeping. Toilets, if anyone needs them, out the door to the right, and then they're on the left. And then the emergency exits are near the toilets. Now, there's normally no questions during presentations. We take them afterwards, but is this an interactive talk, Steve, or?
There's a little bit?
Sort of interaction. Okay, well, just follow Steve's lead on that one. If he asks a question, you're allowed to respond. So yeah. Oh, if he asks for a question, you're allowed to ask a question. That's what I want to say. Thank you to our sponsors, Mantle Group. We wouldn't be able to do these nights without Mantle Group and our other sponsors. Give them a round of applause. Thank you very much, our gold sponsor, and REA Group. Thank you very much. Good work. Some other events that are happening this month. Coding Night, 19th of March. Yeah. It should be fun. I actually don't think I'll be there this one. If anyone else can go, bring their laptop and program, that would be great. Steve?
I'm busy this month.
Yep, okay, great. Someone else. But we do it with GDG as well, so it's sort of just iOS, Android, web, Flutter. Tups can give us a rundown. Yep, okay, great. Social night, last Tuesday of the month, 25th of March. At the Brick Lane Brewery. Brewery or brewing? Brewery? Brewery, okay. Second floor, 466 Queen Street, Melbourne. Great. Other groups, Sydney CocoaHeads, GDG Melbourne, and this little QR code, which is visible, which is great. That has a link to all social, CocoaHeads groups around Australia and New Zealand. So check that out. Great workbook. How to find us, melbournecocoaheads.com and Slack. I think Slack is a good place to talk to us. Yeah. And Mastodon. We got to get on that more. Baz is in charge of that. No, I'm trying to delegate. Okay. Slack channels, jump in, the one specifically for tonight is Melbourne Meetup. So you can, if you're online and watching the stream, you can ask questions there. You can ask them on YouTube. I'm not sure if I'll be able to look at them tonight. I'll do my best. We need help with these nights. Melbourne volunteers. So jump on there and, appreciate any support. If you're looking for a job or want to hire people, go to /jobs. Oh no, #jobs. Speakers. If you want to talk or you want to hear someone talk and suggest something, jump onto speakers, #speakers. Now, I think we have Steve. It's going to be great. Oh, no. Okay, do you want me to run across and do that? You're up, buddy.
Thank you, Pat. How's the volume? Is that okay? Welcome, everybody. Thank you for coming, and thank you to all the people online watching. I guess we've got a bunch of Richmond supporters in the house because there's no point going to the G, right? So Today, we're going to talk about relational databases and SQL. And it's great that everyone's just not running away from the exit because this can actually be interesting. I'm going to try and make it fun. We're going to do a fast kind of run through and get you thinking about what a database can do. To begin with, I wanted to tell you some things about me that you may not know. I've been writing mobile apps for longer than Apple have, and before we had UX designers, clearly. Started in the late 90s, writing on Palm Pilot, and I've been writing these things ever since. I enjoy cooking a lot, especially on fire. American barbecue, Indian curries, cheesecakes, beers. You can tell that I'm such an athlete with that hobby. And all these bottom slides, I'm field hockey fanatic, so have traveled the world watching the sport. This is World Cup in India, in Bhubaneswar, and that's us hanging out with some hockey-roo superstars. Yeah, great. If you wanted to contact me and ask me some questions, the best place, to be honest, is the Mantle Slack. Very easy to find there. If you really want to, you can find me on that terrible social kind of network that we all have to use, but I don't do anything on there. I'm on there because I'm kind of forced to be. So what are we doing today? We're going to talk about these relational databases. We're going to talk about the history. We're going to go into computer science history, which is actually really cool. This is my favorite part of this whole presentation. We're going to talk about some SQL basics that I would expect most of you guys to know. And then we're going to talk about some of the cool things. We're going to look at how we can make SQL work for you. And finally, because it's CocoaHeads, we're going to talk about how we can integrate some of these concepts into iOS. Now, just like A-Train here, we're going to be running really, really quickly through this presentation. This is not a tutorial. Please don't try and make notes. Please just think about things if you want to ask questions or hit me up on Slack. Very happy to help and answer questions as much as I can. Very happy to share my slide deck afterwards. But this is like fun, fast overview. So the idea is that we just think about things. But one of the questions, because we're at a mobile meet, that you might have in the back of your mind is things like this. Are we just using our database for storage, or is it our app's secret weapon? As our app scales and gets bigger and introduces more complexity, where are we doing this complexity? Are we asking our relational database, our very, very fast, performant relational database to do the work? Or are we kind of bringing this into application code and writing .map, .reduce, all that kind of stuff? We probably shouldn't be doing that, is my opinion. So we're going to start with the history of SQL and relational databases, which is pretty cool. And this goes back to the 1970s. And this is where some of the people my age will go, oh, cool. Pryor's going to use popular music to illustrate his timeline. And other people will go, what? Who's this? London Calling? What do you mean? I'm going to give you a link to a Spotify playlist at the end, so you'll know what's happening. So we're going to start with this guy, Ted Cook. He grew up in Dorset in England. He was a serviceman during the Second World War. He was a pilot. He flew these big seaplanes, kind of aerial reconnaissance planes, looking for submarines, I guess. And he had a distinguished career there. And after the war, he moved to the States and got a job with IBM, where most of these computer science history figures began working. So in 1970, he's now working in San Jose in California, and he published this paper, A Relational Model of Data for Large Shared Data Banks. And at the time, there were databases. There were hierarchical databases, and if you wanted to get data out of it, you had to hire a programmer, someone like us. And they would make not an app, but a program to get the data out of the database. Which Cod said, I don't think that's really the best ideal. Why don't we do something where we can allow the user to get the data out of their database themselves? He penned this paper and introduced the concept of relational data and normal forms. Normal forms today we would call a table. And at the time, his paper was kind of met with a little bit of skepticism, even derision from his colleagues. However, it was eventually awarded, he was awarded for this paper a Turing Award. And some sources, if you look this up, call this one of the most transformational papers of the 20th century. So it was pretty important work. So his idea to make data accessible to everyone was to write queries like this. So, yeah, I don't know if there's any relational algebra scientists in the room, but that's pretty cryptic, right? Today we'd probably write it a little bit more like that, which is a little bit more readable. So we meet these two characters, Boyce and Chamberlain. They were also IBM employees working in research, and they were inspired by this work. And they decided that this algebraic kind of expression was still too complicated. There should be a better way where users could access the data without having, training in degrees and mathematics and computer scientists. So they worked away at IBM and they made this project called Square, specifying queries in a relational environment. This was their first goal at simplifying the previous work, but it was still too complicated. So they had another goal. And they came up with this thing, structured English query language. They took the Square ideas and they basically applied like an English kind of declarative approach to pretty much come up with what we would recognize today. And they made this acronym SQL. But SQL had a problem. It was trademarked. So they were embroiled in this long legal dispute. So what they decided to do was basically nuke all their vowels. And they came up with SQL. And this is how we have structured query language. Structured query language is pretty cool. It's declarative. So we've got a lot of Swift UI, Jetpack Compose users in the room. We now write our views to be declarative. We tell the system what we want, and it does it for us. SQL is exactly the same. We tell it what data we want, and the system produces what we need. So in the later part of the 1970s, SQL was implemented by a company called Ingress, which later became Postgres, which many of you would be familiar with. They're still around today. And there was another company involved who used this called Relational Software, who later became Oracle. So that was the two kind of pioneers of the relational database. Now, also in this time period, we've got this character, Tricia Salinger. She's an IBM fellow, ACM fellow. Crazy, incredible work this lady did. She wrote a pioneering system called System R, also for IBM in San Jose. And basically, her work was looking at the cost-based query optimization of executing your query. So you declare a query and you execute it. Her work decides the best way to return that data for you. It's basically looks at the overall processing cost of the different relations of the data and the machine, and it still is really used today in every single database system in the world. And it's really great because she's one of, when you look back in 1970s computer science, she's one of the few females that you can find in a kind of old man, stuffy environment. So we've had the early development work. Now we go forward into the 1980s. And in the 1980s, everything was to do with the commercial advancement of these relational database systems. So we had the first kind of standard. We had SQL 86, the first kind of ISO type standard. And that led to kind of commoditized commercial SQL-based databases dominating the industry, replacing the old-fashioned hierarchical databases. Salinger's cost-based optimizer, this work that she did on System R, became the foundation for SQL query planning in almost every modern database. And we had some commercial databases released, like IBM released something called DB2, and Oracle and Sybase and Informix emerged, making relational databases the standard for enterprise. If we shoot forward to the 1990s, we still got no mobile yet, right? Because there wasn't really much mobile happening in the 1990s, but databases evolved to support networked applications. So we've got things like SQL Server from Microsoft, Postgres, which came out in 1996, and MySQL, 1995, starting to gain commercial traction. We also had some small-scale, lightweight databases. Berkeley released a database in 1991, which were like embedded databases, but still nothing really suitable for our field of mobile computing. 1990s, late 1990s also saw the first kind of research into NoSQL alternatives. Don't talk to me about Mongo. So now we go forward into the 2000s. So it sounds like we're getting pretty current. That's still 25 years ago, right? A quarter of a century ago. And we meet this guy, Richard Hipp. So he grew up in Georgia. He's working for AT&T, and he was working on a contract for the US Navy on destroyers. And they were looking at how they do damage control. So a modern warship is pretty complicated, right? I don't know if anyone's been in some of these old ones at Sydney and stuff. They're full of pipes and wires and everything, right? So when something happens, if they get damaged, they're simulating an exercise, pipes are going to break, wires are going to get severed, and they have to reroute all those services to keep the ship operational. And the way they do that is by putting in all that information into a relational database. So when some pipe gets blown up, they can ask the database which valves they need to change and all that kind of stuff to reroute all the services to keep the ship operational. So they were running an exercise, and the ship was all damaged, right? So it's all the pipes are broken, steam's coming out everywhere, it's on fire, it's sinking. It's kind of something that we would call a P1 incident. People are getting hurt, people are drowning, it's really bad. So they go to the ship's database and say, well, how do we fix this? What valves do we need to change? What do we need to do here? And they got this kind of error, which obviously didn't help the ship. So this guy, Richard Hipp, a kind of brainwave. He said, well, all this kind of stuff's happening. It's chaos. People are dying, the ship's sinking, and we've got this kind of scenario going on in our ship. Why do we need that? Why do we need a server? Why do we need links to a server? Why can we just not talk to the database? And in fact, why can't we just move the database into the client? There's no connections, no cables, no network. And in year 2000, Hipp was on a furlough, and he decided to implement his own database to do this, which of course is this product here. So it's only been around since 2000, right? And I've not said its name yet because there's controversy over how you pronounce it. So we're going to have a quiz. There's kind of four ways. Who thinks A in the audience here is what you might say for this product? Yeah, want a couple? Johnny? Yeah. What about B? A few more? C? Oh, C's popular. C's popular. What about D? Barry's got D. So of course, D's the answer. Well, if you want to go by its creator. It's SQLite, and he says, like a mineral. It's not changed my mind. So if you start, but if someone pulls you out for calling it SQLite, you can say, hey, this is the real name, right? So like a mineral. So what is SQLite? Well, it is a small, fast, self-contained database. In fact, it's so fast that it's often faster than the file system of the platform it's running on, even today. It's cross-platform. It's mostly standards compliant. It's public domain. There's no license on this at all. It's totally public domain. And it's probably now the most widely deployed database ever. That's our history. So now we're going to go forward to the 2020s. I won't quiz anyone on who all these bands are. And we're going to cover SQL basics, which I'm sure many in this audience will go, yeah, I know all this SQL basics. We're going to go through this really quickly. We're going to talk about tools, schema, primary keys, select, joins, filter kind of things, indexes, and transactions, because everyone loves transactions, isn't that true? It's an in-joke, sorry. So how do you deal with it? How do you use SQLite? Well, you need some kind of client, right? So I'm going to recommend 3. Because if you Google, you'll find 300, but most of them are not very good. So a couple that are good, you can use the terminal. So if you open your Mac and you type SQLite 3, you're going to be running SQLite. You can do things. You can run queries. You can create tables. You can create databases. It's pretty hardcore, right? So you're not really going to do that. However, we will come back to the terminal because it has some really clever uses later on. A good option if you don't want to spend any money is DB Browser for SQLite. This is open source. You can download the source on GitHub and compile it yourself. Its UI is a little bit, not quite modern, but it does a job. But it also has a really good trick in that it can support encrypted databases. So if you're dealing with SQL crypt or something like that, you can use this to put in the encryption key and get access to an open database, which most of the other ones are unable to do. If you want to spend some money, I like this one, SQL Pro for SQLite. It's modern, kind of full-featured. You can buy it on the App Store or get it direct, but it's expensive, right? It's $90 for a lifetime purchase. So schema. Everyone knows how to do this. You can create a table. SQL is insensitive. I'm going to just call it SQLite. It's case insensitive by convention, but we generally make tables with lowercase, so in singular. Compound words, I think database convention is you use camel case, but application developers tend to use camel case. Doesn't really matter. You can choose what you like. I prefer to use camel case myself. And you define the name of your columns and the column type. So there's 5 types, only 5 types. You can have null, integer, real, text, or blob. Integers are scalable. They'll go from 0 to 8 bytes automatically. Reals are 8-byte floating numbers. Blob is kind of binary, It'll store what you put into it. You notice there's no dates. There's no date type. So you've got to store the dates in a way that is convenient to you. Most people use this kind of ISO text format because it's human readable. People can understand what that means. You can also use Unix time, seconds since 1970, or you can use Julian day, which is probably slightly more accurate if you really need precision. If you've got a choice, and particularly if you're integrating with a mobile platform, I'd probably consider Unix time, because you don't need a date formatter to exchange it into a date object on the platform, right? You can use this time interval since 1970 call bang. You don't need to care about possibly malformed text inputs and stuff. You're going to get a date. Also remember that in your database, you should always store your dates in UTC. Apply time zones and locale formatting when you present it, not when you're storing it. Always store it in UTC and you won't have any problems. I did deal with a small production incident where a customer got confused because they were in Queensland with no daylight saving and wondered why a transaction was on a different day, but it was their problem, not ours. Now here's a funny thing. SQLite is not strongly typed. So all the mobile engineers, TypeScript engineers, well, they go, oh my God, this is unbelievable. Can't deal with this. It's not strongly typed. So for example, if we made this table, so I've got this account, and I've made this kind. It's an integer, and I'm defaulting it to 0. But down the bottom, I've got 3 queries that I'm running. One sets it to an integer of 1, one sets it to a string of 1, one sets it to a string of hello world. These are all legal queries. You run those, all those values are going to go into the database. Even though you told it, I wanted an integer. SQLite doesn't care. HIP calls this a feature. He calls it type affinity, which a lot of databases use, but SQLite is a bit loose about it, right? So we can run all these kind of queries, and it might be a little bit small to read, I'm sorry, but you can run all these various queries, and type affinity means that SQLite will do its best job to try and transform the data into the column type that you've asked for. So if you give it, for example, as it says there, 42 as a quoted string into an integer column, it's going to turn it into an integer column automatically for you. However, if you give it hello world, it's going to give you that string. If that freaks you out so much, you're going to, this is just crazy, I couldn't use something like that. When you declare your schema, you can apply the strict keyword, and then it becomes type safe. And in fact, it behaves more standards compliant, like Postgres, MySQL, SQL Server, etc. It's kind of rare to see that, but it's a good sanity thing. You can also see here, we can tell our columns that we want something to be not nil, and we want to give it a default value. So if our insert query doesn't supply the value, we're going to supply this default value. These can be useful, obviously, when we're going to get this data into our domain models, if we want to minimize optionals in our domain. And we've got primary keys. So a primary key is a form of index, and it gives each record a unique identifier. And because we explicitly define it as a primary key, SQLite will do a job of making sure that it's unique for us. So that's pretty important, right? You almost always would want a primary key on your database. If you've got a simple table, integer primary key probably does the job for you, and I'll explain why in a moment. UUIDs are obviously very commonly used as well, usually stored as a lowercase string. If you have a very small table and you're using UUIDs and the records are small, so there's not that many columns, or the column content is not very large, probably less than 8 kilobytes, you can apply this without row ID, and that gives you some optimization to make the storage space a little smaller and the queries a little faster. Which kind of key would you choose? Well, it depends. Integers actually take less space. Their lookup performance is a little faster, and they're a little faster, quite a bit faster to insert. However, UUIDs allow you to do obviously offline creation without worry of conflicting with other clients making keys, and it gives you data privacy. So you still see some systems today that use integer primary keys as part of their URL, and of course it allows you just to increment them and look at all these other records. I would say for all but our most simple table, use UUID, and probably you would store it as a blob just for a little bit more storage space efficiency. So now we need to look at joins. So usually the relational table, we've got multiple tables, we want to join them together. Well, how do we do that? Well, let's make an account table. And here as well, sorry, gone too fast, but let's not worry about that. Let's not do this in our applications. Annie, let's not do this in our applications. Right? Let's not select a lot of data, bring it into our application, and then do application code to manipulate the data. It's too slow. Make the database do the work. Remember these questions I asked at the very top to keep in mind? Make the database do the work. Don't do this. Instead, we can write a query. So we can join. We can only return the columns that we need to go into our domain model. We can change the names of columns to match our domain model properties. And we can order things. We can coalesce null values so that we don't need an optional in our domains. So we can make the database do a lot of this work, make our domain models nice and simple. So for joins, let's say we wanted to add an account type. So let's create another table there that we're going to join in, and we're going to insert a couple of records. And we didn't have to specify an identifier for this insert query because it's the primary key. Will insert itself. And here Both tables contain a column called type, so we need to disambiguate between the two. So we use usually table aliases, these little letters. Makes it just a shortcut for us to type. But queries, joins theory is pretty complex. SQLite only supports 3 types of joins, left, inner, and cross. And to be honest, you're only ever going to use left. 99% of the time. You're only going to use a left join. So what that means is you're going to get all the records on the left table, and the columns from the join on the right that match whatever you're joining by. Very easy. And we can filter, so we can get a subset of data. This is good for data security as well. Only return the data that your model needs. So of course we can use a where clause. We can add, we can add and OR them together. We can use equals or, greater than, less than, all that kind of stuff. And we can combine them all together to make compound where criteria. Also, we can do comparisons, all that kind of stuff. One interesting thing when we're dealing with SQL queries is, you would have heard of this, we have to avoid SQL injection attacks. And what does that mean? So imagine you've got a UI with, you're asking someone to enter their username, and you've got some smart little cookie who enters that as their username. If you followed this query, if you just added it to your string that way, well, you've lost your accounts table, because that's running 2 queries, and it's going to drop your table accounts. So what you have to do is use parameterized tables that protects you from this. So be very careful of that. GRDB, which I'm going to talk about later on iOS, also lets you use string interpolation for this if you want to do it nice and straightforward. But I would still kind of use parameterized queries. Indexes. Indexes, super important. All SQLite indexes are balanced trees, and that allows you to look up data using a binary search. So basically what that does is it has a kind of separate table that's hidden. It's going to do a binary search to find your index, and then it's going to do a binary search to find the record in the table. Much faster than using a table scan. You can also use multi-column and partial indexes using where. So if you've got a very large database and you want to limit the domain, you can use where as in your index definition to get a subset of that. Say, for example, you had a multi-tenancy application, probably not pertinent to mobile, but that would be a good use of that. When we do a where clause, it's important because we're looking up records in the table, and if we don't have an index, SQLite is going to do a full table scan. It's going to just basically iterate through every single record and find the ones that match the criteria. That takes a long time, whereas if we have an index, it's going to do the binary search much faster. We can also do multiple column indexes. So often we'll see people writing indexes, sometimes, hopefully, on their tables. And sometimes they'll write multiple indexes on their tables. That's all really good. However, then you look at their implementation, and they're always using kind of where, this, and that, all these 2 indexes together. So what happens if you're requiring it to use, say, 2 indexes? It's doing an extra binary search. It's doing 1 binary search for the first index, another for the second index, a third to find the records. If you do a multi-column index, you're reducing that by 1. So you're getting significant performance gain. If you are doing multi-column indexes, it's one of the only times when you're running a query that the order of elements is important. Salinger, the lady who we met before, her pioneering work means that it's deterministic. So her kind of cost algorithm figures out the best way to get the data. But in the case of a multi-column index, we have to give the where criteria in the same order as we declared the index. Otherwise, it just won't hit. Transactions. So we're talking about database transactions, not any other kind of transactions here. Transactions guarantee an atomic operation. So they make sure that something you do within a transaction is either going to succeed or it's going to fail, and you can roll it back. So a lot of circumstances when we need atomic operations. So for example, Aurelian at work might pay someone on his app, and we're going to take money from some database and give it to some other database. You need that to be atomic, right? We don't want one half to succeed and one half to fail. It's also great for performance because it isolates the I/O of the database on the disk and gives you some performance gains. It also gives you concurrency control. So if you have a multi-threaded access to your database, because SQLite is single-threaded, however, it can operate through a database pool to give you multi-threaded access. Transactions give you better concurrency control and data safety. Transactions are super easy in SQL. It's basically, there's a begin transaction and a commit statement that you top and tail your statement with. In GRDB, which we're going to talk about shortly, everything you do basically inside the closure is automatically a transaction, which is good. We don't really have to do anything. So that's all the basics. I'm sure everyone's, oh, I knew all that, Steve. Come on, what are you doing? Tell me something new. So how can we make SQLite work for us? Let's do some cool stuff. We're going to look at these things. Query analyzer, full text search, generated columns, aggregate, CTEs, you name it. Let's go. So the query analyzer. So we spoke before about the query being declarative. Just like SwiftUI, just like Jetpack Compose, you specify what you want, not how to get it. And Hip, who made SQLite, he's got on the bandwagon, and he calls the query analyzer now, he's quoted as saying, oh, it's AI. That's bullshit, it's not. It's based on Salinger's pioneering work. That's all it is, cost-based analysis. So I showed you one of the tools you could use was the terminal on your Mac. You know, why would you use that? Well, here's why, because most of those graphic clients don't allow you to very easily do explain query plan. So you can see here, I'm prefixing my select query with explain query plan, and it's telling me the result of that is it's going to scan the account table. That means it's going to iterate through every single row in the account table to find the results of my query. And then you can see on line 7, I've created an index on the type column. And when I run that command again, it's going to say, yep, we're going to search using this index. So now we've got binary search. Nice, cool. Don't know, is that like a bubble thing we were speaking about before? Don't know. Sometimes the results of this in the terminal are a little bit cryptic. If you copy paste them into ChatGTP or a LLM of your choice, they usually have a good stab at interpreting it for you, giving you some clear actions. Full text search, really cool. Modern SQLite uses full text search version 5, and it allows you to do as the name says, but it's many magnitudes of times faster than using like queries. It also allows you to do a whole bunch of really smart things we'll talk about with different tokenizers and things like that. Ranking, all that kind of stuff. So here's a couple of examples. We've created a virtual table, merchant underscore FTS5, and we're giving it a specific tokenizer to use. We're going to insert some data. And what you normally do is set up a trigger from your core table. So in this example from our merchant table, every time a record would be inserted or updated there, we would update our full text search index. And then we can run all these kind of crazy queries on the bottom here, and that can become really powerful and very performant. Some of the things you can do that are pretty good, like stemming, you know, so coding, that you can get a match for that. And proximity search, where we start talking about word vectors and how close they are to each other, getting matches there. Even you can apply different tokenizers, so you can get things like search and allow for the customer to make a spelling error and still return them usable data, which is pretty cool. Generated columns, these are pretty cool. So see that, we've got another create table statement, but down the bottom there, we've got, oh, something's different there, right? We've got this account thing. I don't know why I keep doing these banking examples, but we've got this overdrawn column down the bottom, and it's generated always. Well, what does that mean? This is a generated column. They can be virtual, which means they're computed when you do the select read, or they can be stored, which means the value is actually written when the row is inserted. But basically, it kind of gives you almost like a lazy read-only property that we might implement in our domain models in the database. Remember, one of the questions we were thinking about at the start was saying, are we asking our database to do the heavy lifting for us, or are we doing all this work in our application code? You know, some engineers might make an error in their application code. And we can do aggregates. So your query can do all this kind of cool mathematical aggregation. There's a whole bunch of them. Here's just some. You can do averages, you can do counts, you can do standard deviations, sums, you name it. Group concat, that one at the bottom, that's a pretty cool one. That can give you all the non-null values and concatenate them by y. So if you want a comma delimited string of a bunch of values, that's a good example to do that. CTEs and recursive queries, these are pretty cool. Common table expressions are kind of like views. They're kind of like a separate temporary query that will run with the select statement, but prior to it. And recursive versions of CTEs allow you to walk a hierarchy and aggregate data. Let's have a wee look. So imagine we've got a category table, and in our category table, we've got an identifier and we've got a parent identifier, right? So we're now modeling an unlimited kind of tree hierarchy here. Unlimited levels deep. And we're going to put an index on it because we remembered that indexes really help our performance. And let's imagine that we had this other table called transaction, and it's got a category identifier in there. And we've got a requirement that we want to report our aggregate transaction totals by our top level categories. So our top level categories are those that don't have any parents, right? So we could have a transaction whose category is like a third level deep child of a top level category, and we want to roll all that up and ask for the totals. I don't know who wrote that amount typo there. I'm going to blame ChatGTP. So here's an example, and I know there's a block of code, but I don't want people to try and kind of grok it, but the top half, line 1 to 12, is the CTE, and this is like the pre-query that's going to run before our select statement. We're telling it it's recursive at the top, which means this block here is running recursively, and it's going to loop through, it's going to basically walk that hierarchy and group everything together and give us what we want, our sum of transactions by our top level hierarchy. Now, okay, what have we got here? We've got 23 lines of code. If you said, you know, I don't want to do that in the database, I'm going to do this in application code. Well, what are you going to be doing, right? You're going to be writing some kind of recursive Swift function that does all this. It's not going to be pretty. It's not going to be anywhere near as performant as this is. And I would argue not as easy to test and guarantee the outcome of. Last cool thing, window functions. So these are pretty cool. So imagine that, so it does things like can kind of collectively query data through a window or a subset of the records. So things like a rolling sum or a rolling average, a partition of the data can work really well. Here's an example to make it a little bit easier. Say, for example, we've got a whole bunch of transactions in our banking app, and we want to figure out what the daily balance is every day. We can just run this. So this block in here is our partition, and that is giving us our basically daily average with 9 lines of query, all spaced out and nicely formatted, compared to, you know, imagine doing that in application code, right? That's probably going to be a little bit more of a pain. So that's some cool things. Now, we're at CocoaHeads, so we'll do a little bit of a discussion about iOS, but also applicable to Android, I'm sure, as long as you don't use Room. why would you even consider a relational database in your app? Well, apart from the fact we're saying, hey, you can get it to do all these other cool things, not just store your data, but there's concrete advantages, right? You're looking at its performance. It's optimized for read operations. It's got minimal memory usage. If you have a very large data set, for example, you can ask it to supply a cursor where you can iterate through literally millions of records without loading everything into memory. Very, very efficient, minimal CPU use. As I said at the start, on SQLite's site, they've actually got some benchmarks that do show that these kind of queries can be more efficient than file access on the platform, which is kind of crazy. Security, obviously, there are a whole bunch of open source and commercial packages like SQL Cypher, so you can have an encrypted database. There's no network exposure to access the data if you happen to have it cached on your device. And that gives you fine-grained, super fast access. You can have complex relational data. So, we might have an app where we say, oh, we'll just use a P list or something, right? But as soon as you've got two P lists, well, how are you going to join and relate the data together? A database is built for that. It's going to do it really, really quickly and support complex joins, views, temporary data, CTEs, all that kind of stuff we talk about. And it's got this high-performance query planner. This Salinger's work that we still use today. Everything works fast. It's deterministic. Really, really cool. It's offline first. So we've got an application. We've got our data cached on the application, and we go on an airplane, or we go on a tunnel, or we go on a shopping center. Most things still work because we've got full access to our data. We've got we can implement conflict resolution strategies, eventual consistency, all that kind of stuff. A lot of these packages are going to give us adapters and codable conformance. We want to use ORMs, all very good stuff. It's also cross-platform, and theoretically, if we're doing an iOS and Android app, there's no reason they can't share the same database schema, even the same queries, and have that done once. Also work on core data and things like that, or Swift data if you really want to give yourself a headache. I would recommend this package called GRDB, which we'll explain why in a moment. It's pretty cool. There's a couple of alternatives. SQLite.Swift is a smaller, easier wrapper. Because SQLite you could run directly, but it's C. It's a C interface. So you could write your own code to interact with that, but that's a bit masochistic. So we use a wrapper. SQLite Swift is good. Some of the older guys might have used FMDB back in the Objective-C days. That was the kind of go-to wrapper for SQLite back then. But GRDB is pretty cool. It's open source, MIT licensed, actively developed and supported. It supports all our platforms, distributed through Swift Package Manager, really good documentation, and it does a whole bunch of stuff. It's got ORM kind of functionality if you want to use it with seamless codable conformance, but it also supports raw SQL queries and Swifty kind of query interface if you want to go that way. It supports Combine and Swift concurrency, really good multi-threading support, and it does some really cool stuff. It supports migrations, the full text search, CTEs, all that kind of stuff. It's really easy to set up. There's a bunch of code in here from GRDB's website. Don't need to understand it, but I mean, it literally is a dozen lines of code to implement. Set up a record type with some conformance if you want to use the kind of ORM route, and then bang, you can fetch them and write them with very, very little code. You don't have to write your own codable conformance in most cases. I personally usually kind of refactor this into some kind of GRDB storage service type class where I can initialize the database in my service layer or whatever. Very, very easy stuff. It's got helper methods for really good migration support. We'll talk about shortly. Really, really simple. You can start your database from a migration to begin with, or you can put if you had a fixed schema, for example, you could put a empty database in your application resources and copy it over. Very easy. And you can instantiate it using either, you'll see in the documentation if you dive in there, either a queue or a pool. They suggest a queue. I would probably suggest a pool because probably we would want to do a more rich application that needs multi-threaded support, which a pool allows you to do. So that opens the database in write-ahead logging mode. So for example, that will allow you to support concurrent read operations, get better performance. Query interface, you can conform to all these different types, record type, table type. Makes it really easy if you want to go the Swift route. Also, you can use raw SQL if you're more familiar with that, which is really cool. And it supports value observation, which is just, this is amazing. This is actually a SQLite feature, but GRDB exposes this so well. What that does is imagine that we've written a query, and we're going to select everything from our account table. And that is, we're going to run that query, and it's going to give us some kind of record set with some account records, which is all really good, right? But ultimately, somewhere over in our view model, we've got some kind of published property. So I've got it in some kind of loading enum, but I want a published array of these account records. So how do I do that? If I add this value observer, this is going to observe any changes to the output of that query and publish a new value, which we can subscribe to, which will go into our published property. And that's going to give us a reactive view layer from database changes, which is pretty cool. How do you do that? It's pretty cool. This is how you might choose to do it in Combine, which is all pretty simple. One new thing is the ability to share an observer, which means if multiple areas in your application are observing the same query, you can share that, only do the work once, which is pretty cool. It also supports modern Swift concurrency with async throwing string. Syntax is a little bit more convoluted, but does a job if you don't want to use Combine. I usually kind of bring all that together. So we've got some kind of storage service that we've made. It's conforming to one of my repository protocols here, and I've made like a function that's going to get all my stores, and it's calling a function in my database. I'm extending GRDB's database, and that's given me nice separation of concerns where I've put in my query using either SQL or the Swifty syntax to do the actual work. What that means on my view model is that I can make published property. So I've got my loading state enum. I've made a published property that is going to give the data to my view layer. And I've made a property to do my publisher, which is all pretty straightforward stuff. And then I can just subscribe to that. So what's going to happen is that every time I receive a value, because the value observer is going to emit a new value every time the results of the query change, I've subscribed to that. I'm going to set it to my items property, and my view will update. Getting to the end of the road here now. What are we talking about now? Custom functions and aggregation. These are really cool. So GRDB allows you to do a lot of powerful stuff with SQLite. You can add custom functions, and you can write these custom functions in Swift. So here I'm writing this function metaphone, where I'm going to do like a fancy lookup for mistyped search criteria, basically. And I've got this pretty simple syntax where I can call my class that's doing the work. This is all just pure Swift. A little bit of boilerplate around the top on the argument count. This pure thing just means that if we set that to true, we're telling the SQLite query cost analyzer, Salinger's thing, that if it wants, it can optimize our query, give us better performance. We could set that false, so we didn't want it to do that. And yeah, so it's pretty easy, you know, taking an array of database values, Yep, can throw, all that normal Swift stuff. How would you use that? Well, when you instantiate your database, this is the code we just looked at with the ellipses there. And then when we can create a configuration to add any custom functions we like, and then when we instantiate our database pool, we give it the configuration. What that means is that we can now use that custom function in our queries, either raw SQL queries or the Swift syntax queries, which is pretty good, right? Because without that, and if we wanted to write a custom function, we're going to look at our C handbook and figure out how to write C and compile it into SQLite, which isn't fun. We probably don't want to do that. This makes it very, very easy, and it's quite performant. Let's talk about migration. So we always have migration. So that migration means your database schema is going to change. Could be adding tables, adding columns, adding indexes, all that kind of stuff. GRDB makes that super easy. We can make a class, and we can add just basically a migration like this, where we can use either, again, the Swifty syntax, or we can use raw SQL. Makes it work really, really good. Migrations are cool. The only migrations that run are those that haven't run before. So if your customer even, if they keep running your app or whatever, it's not going to double up on anything. It's safe. As long as we obey a few rules. Never modify a deployed migration. If you need to change it, make a new one. Wrap the migrations in a transaction to make it atomic, so it either fails or succeeds. And if it fails, it would run again. Use consistent strings for your table and column references. So what that means is, like, if we use variables for our migration and then someone changes the source of that variable, your migration is going to change from user to user. You don't want that, so use explicit constants. And there's a little trap. If we create a new column and we make it not null and we do not give it a default value, we're going to have a big problem, because basically that makes old existing records in our table illegal. So we'll basically crash. You can unit test everything. It's really great. You can make a class of a migration and fully unit test it and be happy that it's working. To do it, super easy. You've made a class. You just call it with one line of code. If you want to know what all those album covers were, hey, you can go to the Spotify playlist. Go, what the hell was Prior talking about with all that? Any question? And again, best way to contact me is on CocoaHeads Slack, and happy to take any questions.
Any questions?
Thanks, Steve. Early on in your talk, you talked about how SQLite is not typed and there's no date type.
Yep.
This might be throwing you in the deep end, but how then do we do like those where clauses with giving a date range and so forth? Do you know how it does that?
Yeah, so it has kind of inbuilt support, Nathan, to deal with that. So if you were storing your dates, for example, in that text ISO format, and you said, okay, where date is greater than this, it's smart enough. The query parser is smart enough to understand your intent, and it will do what you want. Yeah.
Is there any reason not to run the optimizer?
I don't think so. I think people